Hi, I'm Dongyu, and I'm a graduate student from Dr. Jeremy Levy's research group in University of Pittsburgh. Today, I'll talk about our effort on generate and detect surface acoustic wave on lanthanum aluminate strontium titanate. Surface acoustic wave is a kind of acoustic waves propagates along the solid surface with its depth comparable to its wavelength. With a pair of interdigitated transducer device, we can create surface acoustic wave and detect it by direct coupling between the elastic waves to the electric field. And there are many applications of surface acoustic wave, such as surface acoustic wave filters, sensors, and surface acoustic wave touch screen. These days, surface acoustic wave attracts many people's attention again, which is because it was shown that surface acoustic wave can play a useful role in quantum electronics. In 2011, two groups achieved single electron transport between two quantum dots using surface acoustic wave on gallium arsenide. With the piezoelectric property of the material, surface acoustic wave can cause such potential minimum. Each of these potential minimum can carry a certain number of electrons and drag it along the nanowire as the surface acoustic wave is propagating. As this diagram shows, they can use surface acoustic wave kicking single electron back and forth between these two quantum dots, which is really exciting because the ability to transport single electron can play a useful role in spin-based quantum information processing and quantum computing. The system we're working on is lanthanum aluminate strontium titanate heterostructure, which has rich phenomena that have been discovered. There is 2D electron gas formed at the interface, and it has tunable metal-insulator transition, superconductivity, magnetism, and tunable spin-orbit coupling. Here I want to focus a little more on the metal-insulator transition. When the thickness of LaAlO exceeds 3 unit cell, the interface is conducting. When it's 3 unit cell or less, the interface is insulating. The system we're working on is 3 unit cell LaAlO on STO substrate, which is insulating but highly tunable. While applying a positive gate voltage to the system, it's conducting, and a negative gate voltage can make it insulating. With these properties, our group has developed the technique conductive AFM lithography in this system, which can be used to pattern nanostructures, such as nanowires and tunneling barriers. To do this, we start from 3 unit cell LaAlO on STO substrate, which is right at this threshold is insulating but highly tunable. When we apply a positive voltage to the AFM tip and drag it along the top surface, it will leave a path of protons. These paths of protons will act like an local top gate, tuning the interface below the path through metal-insulator transition. This process has a very high resolution. The width of the path can be as small as 2 nanometers. And it's also reversible, which means by simply applying a negative voltage to the tip and drag it, you can erase the path. With this technique, our group has created many devices at the LaAlO STO interface. One of them is the single electron transistor. Basically, it's a nanostructure with 2 barriers to isolate it from the source and drain, form the quantum dot in the middle. The chemical potential of the quantum dot can be efficiently tuned by applying this side gate voltage. The quantum dot shows a discrete energy level looks like this, and we use a gate voltage to tune the chemical potential of the quantum dot. When the energy of the electron aligned with the source and drain chemical potential, the electron can tunneling through these 2 barriers, give us a conductance peak looks like this. When we varying the gate voltage, we can get different conductance peaks, which is called resonant tunneling peaks. And in our system, we can see these peaks clearly. Since change the potential of the system can tune the electron transport property of the single electron transistor, can we use surface acoustic wave to change its potential to tune the electron transport property? To do this, we should combine surface acoustic wave into our system. The most common way now to generate surface acoustic wave is using this interdigitated transducer, which is a metallic COM structure. When we apply positive and negative voltage on each side respectively, there will be electric field formed in the middle looks like this. When we apply an AC signal, the electric field will flip its direction back and forth. With the piezoelectric property of the material, these will cause tension and compression inside the lattice. Thus, surface acoustic wave is generated. Usually, the detection of the surface acoustic wave is done by applying a second interdigitated transducer. Since mechanical wave can cause potential difference inside the material, can we use the single electron transistor to detect the surface acoustic wave by using surface acoustic wave to tune its chemical potential? To do this, we design our device looks like this. Combine these two different devices together. We have interdigitated transducer device to generate surface acoustic wave with wavelength 2 micrometers, and we put a single electron transistor in the middle with 0.5 micrometers barrier distance. First, we will apply some simple nonlinearity analysis. We have two interdigitated transducers to generate surface acoustic wave with frequency omega 1 and omega 2. There is a different frequency delta omega between these two surface acoustic waves, and these two surface acoustic waves will propagate at the opposite directions. We put a single electron transistor in the middle, act like a mixer to mix these two waves, and it will give us a nonlinear term looks like this. The lock-in measurement will fill out the high frequency term and left the difference frequency term, and this will be the signal we need to measure. I want to mention that here is a background-free measurement because we didn't give any sourcing signal with this frequency term to the system. So for the experiment, the setup looks like this. We give RF signal to two different IDTs to generate surface acoustic wave. We give a DC sourcing bias passing through the single electron transistor and measure its drain. We use a DC side gate voltage to tune the single electron transistor. For the experiment, we did a comparison between applying the surface acoustic wave and not apply the surface acoustic wave for the control experiment. First, we apply AC plus DC signal to the side gate voltage to tune the single electron transistor. It shows the structure looks like this. After that, we replace the AC side gate part into our surface acoustic wave generator, and we saw the signal looks like this, which is really similar to this. When we compare these two different tuning effects and plot them as the X and Y component, they show a very linear trend looks like this. We believe this is showing that surface acoustic wave is tuning the single electron transistor, and it acts just like an AC side gate voltage. With all this interesting data, we're still facing some challenges for the STO in microwave regime. Bulk STO is lossy and dispersive in the microwave regime with an extremely large dielectric constant at low temperature. In this table, I compared the STO to the sapphire. You can see for the low temperature, the permittivity and the loss tangent for the STO are orders larger than the sapphire. So we're seeking a way to either smaller the STO size or thinner the STO thickness to get a better Q factor and reduce the RF loss. With the help from our collaborators in Wisconsin, we get the sample with freestanding LaAlO STO membrane on top of sapphire substrate. The optical image looks like this. To combine the LaAlO STO membrane into our system, the first thing we need to ensure is it's also writable under the conductive AFM lithography. So here is a writing test of the freestanding LaAlO STO membrane on top of the sapphire substrate sample. First, we use a positive tip voltage and write to connect these two electrodes. Then with a negative tip voltage, I cut these electrodes. Here we can see a clear conductance drop with this cutting. And then we first create a small canvas in the middle with a negative voltage. And after that, we connect these two virtual leads we created, and we can see a clear conductance jump. This is really exciting because it is shown that LaAlO SrTiO membrane can also be a good candidate under the conductive AFM lithography. Also, we believe it can be a better platform for the RF measurement. In summary, surface acoustic wave can be generated and detected on LaAlO SrTiO, and we can use the surface acoustic wave to tune the electron transport property of the single electron transistor. It can act like an AC side gate voltage. After that, we would like to combine the single electron source and the LaAlO SrTiO membrane sample together. Our goal is to achieve the single electron transport on LaAlO SrTiO using surface acoustic wave. That's all. Thank you.